Okay, now so we will I mean any general feedback that we have already done 3 classes, we have had a few quizzes. So is there any general feedback that anybody has before we start with our formal lecture today? Okay, so I'm assuming that everything is going good, and as we have been saying that there are enough TAs and you have my time. So if you have any difficulties, feel free to approach us. Okay, don't let the difficulty build up and then you start approaching us. So that's a bad strategy. So don't fall into that. And at this time of the semester, you have more time. So if there is something which is not clear, you can approach us. Okay. So that's what I would like to announce before starting. And so we were doing the Reynolds transport theorem. So in the previous class, we derived the Reynolds transport theorem and we showed how it is getting motivated from a very simple example of a village and people in the village. And we had seen the small problem from there in the quiz today. And then we also, so once we have understand where the basic statement is coming from, that accumulation is equal to growth plus influx minus efflux, then we it's a matter of just mathematically or putting it in a mathematical form. So that's the next thing that we did in the previous class, and that is what our Reynolds transport theorem is. Now, once we had the Reynolds transport theorem, then we used it to drive the mass conservation and the momentum conservation equations. So this is what we had done in the previous class, and what we are going to do today. So whatever we have derived till now are in the integral form. We saw that there are integrals which are sitting in the equations. So they are an integral form of the mass and momentum equation, which is what we have gotten till now. Now what we are going to do in today's class, first we will take one example and see how to apply these equations, and then we will start with our derivation of the differential form of these equations. Okay, so that's the plan for the next, for today's class as well as a few classes down. That will be coming. So let us recall what our Reynolds transport theorem is. So Reynolds transport theorem, if I just write it out as RTT for short, essentially says that rho by dou t. Okay, we had just used a single integral, so let's use a single integral rho eta d volume over the control volume is equal to dn dt minus integral of rho eta or eta rho vdA eta rho v dot d area, and this is over the control surface. So this is what we had written in the previous class, and we explained that these integrals are over different terms, different things. So one is over the control volume, the other one is over the control surface. So sometimes we use triple integrals. That is what was there in the quiz. Hardly matters. I hope you will be able to, although there's a difference in the notation, but it does not change anything as far as the understanding goes. Now from here, we derived our conservation of mass and momentum. And to drive our conservation of mass, we put eta is equal to 1, and we also said that capital M is equal to, so conservation of mass we said N is equal to M and eta is equal to 1, and we also said dm dt is equal to 0. So then you can see that the equation readily simplifies, and we get dou by dou t is equal to minus integral of rho v dot d area over the control surface. Or if I have to take everything on one side, okay, I can take this term also on the left hand side and equate it to 0. This is of course rho d volume. Okay, and we are using, just to say it is volume terms, we are using a v with the cross in there, and the other one is corresponding to my velocity. Now, we also got the conservation of momentum equation. So, for which we said n is equal to vector p, which was equal to mass times velocity. So, our eta is equal to velocity now, and our dp dt are the forces that are acting on it. Okay, so we substitute all this and we get our okay, so this is what we get. And if we now look at this equation, we say that if we were to look at momentum which is contained in a control volume, that can change because of two things. One, if there is a force which is acting, sorry, this is just force. Yes, so if there is a force acting on it, okay, and the other one is the momentum which is entering and leaving. Okay, so on the right, the second term on the, or the last term in the equation is the momentum crossing the control volume, and this is what we have to be accounted for. Okay, so now we will see that this is a very simple looking equation. It is not as straightforward. So we will actually take, so it's somewhat deceptive as to what is hiding. So we will take one example and we will see how to apply this equation correctly for it. So let us say that we have an object and which is immersed in the flow. So we will take a circular cylinder, a circular object, just for the sake of simplicity, and say that this object is also very long. So it's a long cylinder that is placed in the flow, and what we are interested is finding out is what is the drag on this object. So that's our objective. What is the drag on this object? So we will introduce a method to find out this, which is known as the wake survey method. Okay, and this wake survey method is essentially involves the use of this equation that we have written. So why did we take a circular object? We can take an arbitrary shape object, and you will see that the method will work equally well for that object as well. So there is no restriction on the shape of the object. We are also saying that it's a 2D object, it's a long object, long cylinder which is placed. So it's like a cylinder which is like this. Okay, so this has a circular cross section and this is long, and when we say long, then we are looking at the long with or length of the object with respect to the diameter. Okay, so if L by D is much greater than 1, okay, we will say it's a long object. Okay, so L, and in this case L is I mean, in this case, let us say L by D is at least 7, 8, 10. Okay, so you can see so almost an order of magnitude more. So then that means that if I take any cross section here, and if I take another plane here, if I look at two different planes, I will see identical things happening, because these ends of it are so far away that it does not see any end things. Okay, so that's why we will treat this. So this is the case that we will take, and it's a simple case that we would look at. Okay, so it allows us the assumption of two dimensionality, and circular is just to for the sake of convenience, because that's a lot of times where the object is like that. So what do you expect? So if I look at this problem, what do you expect to happen So, okay, I can, if you want to think about it, what sort of a thing we are looking at. This, as we said, could be an arbitrary object. So, think of, we are moving in a car and we want to find out what is the drag which the car is going to experience. Okay, so the car is my object and there is a flow which is happening. So, here we are moving against the air. We can reverse, we can sit in the car and then we will see air coming towards us, which is the situation that we are now looking at. And we would now like to find out whether the drag which is going to be experienced by this car is going to be significant, that I need to account for in my design. If I look at aircraft, of course, aircraft drag is very, very important, because that's the primary form of, that's what you need to overcome. In the case of a car, maybe you have so many other, the frictional losses and other which will which are more important as compared to the air drag. Okay. So, this is just a physical sort of a motivation to where we look at, where we can find this, and we can see a lot of cases, and we can see a lot of times, we are object and we are just, air is passing by it. We are seeing, unfortunately, a lot of news where people are getting dragged or animals are getting dragged because of the flood. Okay, it's just because of the drag that they are experiencing. Okay, they are in a flowing stream, water is flowing past them, and they just get dragged along with the flow. So, how am I going to look at this problem? What do we expect? So, we will first sort of understand it physically before we start applying the equations, and that is always a good idea. Don't just blindly start following something. First, pause and see what is it, what does it the problem mean, and what will be our strategy to look at it. Hmm? So, there will be a pressure difference. So, if I look at the face here, okay, if I look at a face here, if I look at the face behind, there will be a pressure difference which will be acting on it. Anything else? The velocity distribution changes. So, the velocity here, if I look at, will be less or more as compared to whatever is coming in, lesser, right? That is expected. There would be a region of wake. So, what we expect is that there would be a wake which will be forming behind this object, okay, and in the wake region, the velocity will be less than the incoming flow, right? So, sorry. So, boundary layers will form on the surface of the cylinders, okay, and these boundary layers would be very important. Okay, they will be separating at some point of time if my flow Reynolds numbers is large. Okay, so that will be the dynamics of the and that will affect the dynamics of the wake. So, okay, so we sort of know what we're talking about. So, the first thing, just like in the case of a village, what we did is to say that we are talking about a village. Okay, so that means that we have to isolate certain region. So, what should be the first thing that we should do is to draw a control volume. Okay, and we can see that that is before anything we have to, before we can start applying our equation, we will have to define what is the region on which we are applying these equations. Okay, so let us say that this is the control volume that I have chosen. Now, the question arises, how did I make this control volume? This control volume is arbitrary, and our answer should not change on the control, should not depend on the control volume. Okay, so that is a statement, and we will see how to, what exactly, how do we make sense out of that. So, now as we have said, okay, this is my control volume. Maybe we start looking at what is the type of flow that we have behind. So, we can say that, okay, behind the object there is a reduction in the velocity, and if I were to draw the velocity vectors, this is how the velocity vectors would look like. Okay, maybe we can also give, because we have drawn a control volume, we can give some dimensions to that. So, let us say that this dimension that we are looking at is 2h. Okay, h is with respect to the cylinder. We have put it, used symmetry and said, okay, h is there on both this, either side of the cylinder. Okay, so now what I would say is that we have written down both these equations, although it may appear, okay, when we are talking about drag, okay, which is going to be primarily because of the momentum deficit, or the momentum is just going to be different, okay, and this difference in the momentum will lead to a force, okay, and that force is what we are calling it as drag. So, if I look at this equation here, we can say that, okay, if I am looking at steady state, okay, you can say that this term is not going to be very important for us, or it will go to 0 under steady state, whereas this term, the last term, is what will lead to this force which is going to be acting, correct. So, that's what we sort of understand, and we will have to, so I mean it may appear as if we will have to use our momentum conservation equation, okay, but what you should know, and this is one sort of simple rule that we have to sort of understand, is that before you apply the momentum conservation equation, always apply the mass conservation equation. So, mass conservation equation is always applied first, okay, always, I mean whatever you are looking at, whether you are interested in energy, okay, you still need to apply the mass conservation equation. Although nobody will explicitly say please apply the mass conservation equation, you will always have to apply that, okay. So, if you want, you can make that as a note, small note for yourself. Now, why will that become important? We will see that in a minute, okay. So, let us say that I find out how much mass is coming. So, in this control volume, this much is the mass which is coming in, right, and how will I find out this mass now? So, I will take a small area, this is my small area element, let us say I call this as, so maybe I start putting some axes here. So, let us say this is my x axis, this is my y axis. So, this is my dy. So, this is a small area element dy, and of course, everything I am doing it per unit depth, okay. So, the depth per unit depth, I will assume it's like 1 in along the other direction, so that I don't have to write out anything in that direction. So, my area that the flow is going to see is dy into 1, okay. So, it is dy, and the flow which is coming in, let us say this has a velocity u naught, okay. So, it's u naught times dy. So, this is the amount of volume which is entering this through this region here, small region here. So, if I have to now multiply it by, if I now multiply it by rho, density, then it will become the mass which is entering, right. And then I have to integrate this from y is equal to minus h to plus h, okay. So, y is going from minus h to plus h. So, this is the incoming mass m dot in, and how much is the m dot out? You can see that I will have a very similar thing. So, here the velocity is varying. So, it's, so earlier the flow which is coming in, I am assuming that it is coming in with a uniform velocity, okay. So, in the case of a car, this assumption is not correct. This assumption will be correct if you put the object in a wind tunnel, okay. So, here it will be rho times u. So, here the velocity, let us say, is just simply u, okay. So, it's rho times u, and let me okay, and so times dy. So, in a similar way, you will get exactly the same thing. Is instead of this velocity u naught, capital U naught, you will can write it as u, and y is going from minus h to plus h, and this is my m dot out. So, now what is the first thing that you realize? What is the relationship between m in and m out? Both are equal. Everybody agrees? No, sir. Good. Why do you not agree? Some of the mass has to leave from the sides, and why is that? How do I know that? You can, because you can see that the velocity is, we already said we are in a wake region. What happens in a wake region? Velocity is less. So, the velocity is less if I do an integral like this. Okay, the mass that I am going to get, you can just look at the value of the two masses. So, the value of the mass that I would get here, so here I can simply integrate it and say it is rho times h naught, sorry, u naught times 2h, okay, because velocity is just uniform. I can just take it out of the integral. Okay, here velocity is not uniform, but it is, I know that u is less than u naught. Okay, so this integral will definitely be, and rho I am assuming is constant. Okay, if I just assume rho as constant, rho, which as we will see, we have not yet talked about that, but we will be talking about compressible and incompressible flows. So, and in this course, we will always be talking about incompressible flows where density is always going to be constant. Okay. So, I mean, it is clear that because we are integrating over the same area, okay, and my velocity has now reduced, okay, therefore, the mass that I am going to, that is leaving from this side is less than the mass which is coming in. So, the question is what happens to the remaining mass? That remaining mass has to now leave from the sides. Is this understood? Okay, so if there were walls around the two sides, if this was in a channel, then whatever mass is coming in has to go out. There is no other way because there is nothing that can go from the side. I have already constrained it from a wall. Here I am not constraining it with the wall. So there is no reason for the mass which is coming in should be the same as mass which is going out, because it has already another outlet which is the sides from where the mass can leave. Okay, is this point clear? Any questions here before moving ahead? So now you can say, why did we apply the mass conservation equation first? Because why? Because the mass which is going out from the side is also going to carry certain momentum with that. Correct? So when you look at the momentum balance, you have to account for the momentum which is also going from the sides. Is this understood? And if you don't do that, then of course your answer will not be correct. So how much mass is going from the sides? M dot from the side is equal to m dot which is coming in minus m dot which is going out. Okay, everybody with me? So you can see that this equation, as we said, the term is only one, but there are enough complications in here. Now let us look at, so let us now look at the force. So I will take the same control volume and I will ask you to tell me where are the forces, what are the forces which are acting on it. This is my object, which is somewhere in between. So what are the forces which are acting on it? So don't give me some names, some jargons. Okay, what we are interested in is on this object, what will cause a force here. Okay, so we have already set pressure. So there will be some pressure here, P1, and there is some pressure here, let us say P2. Okay, so if these pressures are not the same, then there will be a pressure force that will be generated. Okay, and how can I show it? I can say, okay, there is some pressure which is here, okay, which is some acting on it, and this side the pressure is acting like this. Pressure we know is always going to be always a compressive force. Okay, so and the difference of this, so P1 into this area minus P2 into this area will give us the pressure force that is going to act on this control volume, right? So I will just say first is my pressure force. What else? Viscous force. So viscous force, how will it act? So on this surface, viscous force will act. Let us say, if I just say that, okay, just draw, okay, or maybe in the more conventional way, we just draw it with the arrows which are down. Okay, and here I will show it with arrows up. And here I will show it with, let us say, viscous force is acting like this. Okay. So you can see that this is where the viscous force is acting. And what is this viscous force going to do? Is of course also going to change. If I take this viscous force multiplied by the respective area and then sum it up or integrate it, I will get the total viscous force which is acting on this object. Okay, and we will see that if I are looking at forces along the x direction, then I don't have to bother about these viscous forces. Okay, I will only need to worry about viscous forces which are here on these sides, right? So I will say that there is some viscous force. Let us say this is acting like this, acting in the opposite direction, minus x direction. Earlier one was in the plus x direction. And what else? So this is the other force that we are looking at. What other force which is there? The drag itself. Okay, weight you can put in, okay, depending on what is the orientation. Okay, but weight will be in, let us say, if it is in this direction, I mean weight, I mean one can consider, but let us say I will not bother about weight for now. I can orient the objects as that the weight is acting in one direction and the force is acting in the other direction. So in the direction of my drag, the weight is not really important here. Okay, so I will, just to keep simple, I will do that. So here I will, there will be a drag force which is going to be there as well. Okay, so you can see that before writing out the, so whatever the change in momentum that we are going to look at, this is going to be brought about the forces which are going to be acting in this manner here on this object, on this control volume rather. Okay. So now let us understand, we said initially that the control volume is of arbitrary size, arbitrary shape, arbitrary size. Okay, now we can see that what would change if I change the control volume. So you can see what is fixed here and what is going to be dependent on the size of this control volume. So let me just make an argument. Let us say if I push these boundaries very far before and very far away from the object, what do you expect to get? You would expect the pressure to go back to wherever it was. Okay, so that means that the pressure force will now disappear. Okay. Similarly, if I make this, so this is where the pressure force is acting on this side. So what we are saying is, let us try to take it very far away, so that then the pressure is now whatever is the earlier pressure that we had earlier, and therefore I will get no net pressure force. So I don't have to bother about a pressure force. Okay, you can see that I want to compute minimum number of things. Okay. Now what about this side? If I put the object, if I take these boundaries further away, then what would happen? Viscous force will disappear. Okay, why is that? The viscous region will be less. Okay, so the other way to look at it is that you can think of, we go back to this picture, and you can say that behind the object there is a wake. Okay, but if you go very far away on this side, lateral sides, okay, the flow is not feeling the presence of the object. Okay, so that means that the velocity here and the velocity here are pretty much the same. Okay, and if the velocity is uniform, then there are no gradients and there will be nothing which will be acting on this side. Okay, so these viscous forces will disappear in that case, right? So now we can say that I am going to assume that the control volume is large enough that I satisfy this. If I don't have to satisfy, if I am not satisfying them, then I will have to actually compute the viscous forces and the pressure forces, okay, which is not going to be necessarily trivial. I will need more information for that to be able to actually compute these forces. Okay, so that is why we will assume that the control volume is large enough and I don't have to bother about them. Okay, so I get essentially by choosing a large enough control volume, we are making these two terms 0 and we are only left with the drag force. Now we can come back and answer how much momentum is coming in, how much momentum is going out, and then the difference of that should lead to my drag. Okay, is this clear? Okay, again, before moving ahead, let me just pause and see if there are questions. Yes.
So if you're moving the upper and bottom bound is very far away, that won't affect the mass. The mass will still be exiting over there in some momentum.
Yes. So the mass will still be exiting, and why is that? Because there is always a velocity region, deficit region that has been created. Okay, as we said, if you look at the integral, okay, h, any value of h that you take, okay, I will, because my average velocity on the downstream side of the cylinder is less than the average velocity which is there on the upstream side, okay, there will be a mass imbalance, and the remaining mass therefore has to always remain go from the sides. So now, okay, unfortunately, I don't have too much of a board space here. So let me say that what is the momentum which is, let us say, momentum out or momentum in, let us say. So I'm going to find it out from this term here, V dot d area into velocity into density. Okay, so here what is coming in is very straightforward. It's because everything is u naught into let us say dy into rho into u naught and integral of this. Okay, of course we have to be careful where we are taking the components. As we have said that this is a vector equation, again we need to deal with it carefully. Okay, sometimes people write this without understanding and they get it wrong. Okay, so here we are looking at force which is along the x direction. So force which is along the x direction, this we have already dotted it. Okay, this is a dot product, no issues, and velocity component has to be of the x component side has to be taken for finding out the force along the x direction, something which we had said in the previous class. And this is going from y minus h to plus h. Now the mass which is momentum which is going out, okay, from the right hand side you can see it is rho times u times dy, okay, this is, and then so u here and minus h to plus h here. Okay, so this is the momentum which is coming in from the left hand side, momentum going out from the right hand side. But as we have said that there is momentum which is also going from the lateral sides, mass which is leaving and the momentum which is leaving along with that. So momentum from the sides is going to be the mass which is going from the sides multiplied by the velocity with which it is going. And what is the velocity? So we have assumed that this is far enough. Okay, and we are in the free stream region again. It is there in the uniform flow region. So we have, therefore, we are saying it is u naught. Okay, so now we have all the components, just put everything together and hopefully you should be able to get everything right and get that the drag force so F drag is equal to rho u naught square times integral of u minus u naught 1 minus u by u naught dy minus h 2 plus h. Okay, so I'm just putting everything together. We have all the equations with me, and we just put everything together, and this is the drag force that we'll find. Okay. So questions here.
Why had we taken U naught?
Because we said that this is a far enough that the velocity that is being experienced by the flow is actually u naught. Okay. So again, what is important here is you can see that in a simple problem like this, we had just looking like one term is 0, there is only 2 terms, and that's it. But you can see that there are a lot of intricacies when you actually start applying it. Yes.
So if I change the shape, it will not affect this equation.
So these equation, okay, so that's a good question. So how does, if I change the shape, then what happens? The analysis does not change. Okay, so what will, would I know that my object has changed? Change in?
Limits.
Change in limits, no. Why should I change my limits?
Velocity profile will change.
Hmm?
Velocity profile will change.
Velocity profile would change. So that means the distribution of u would change. Okay, so this u will change automatically. So my drag force that I will get will be different now. So u is changing now. If I put, like, let us say, a different shape object, I will get, so let us say I have chosen a very large control volume anyways to begin with, and then so, and then if I, let us say, put a plate which is aligned with the flow or plate which is perpendicular to the flow, okay, I can see that my velocity distribution that I will get. I'm just taking this extreme example so that you can see even the same object I have just oriented in a different way. The wake region is now becoming different, and the velocity distribution is becoming different. So that is why the drag force that you would find will be will be different in the two cases. Okay, so that's a very good question. Yes.
And then, so the wakes that are forming, they have a particular pattern or frequency. So can we use these same equations to find that frequency, or is it something else?
Okay, so that's also a very good question. So there, the question that is being asked is that we normally have vortex shading, okay, and I hope you remember carbon vortex forming behind the object, okay, and the object will start oscillating if you just leave it. Okay, so the question that is being asked is, how do I handle that? Can we handle it within the same framework or not? So the thing is, just remember, so there is nothing wrong with this equation. We have said that these are very generic equations. There has been no assumptions that we have made. Okay, so there is absolutely no issues as far as using these equations for even that problem goes. The only thing is that you will have to, if everything is time varying, then you have to be more careful. Okay, you have to apply it with lot more care. You cannot say that, okay, the momentum, this term we just neglected it. Okay, this term will start appearing now. Okay, the momentum that is going to be there is going to be appearing into your equation. Okay, and again the masses which are leaving, etc., on the two sides, okay, that will also become a function of time. Okay, so everything now becomes a function of time, but if you compute everything correctly again, you will get exactly the same thing back. But here, the drag force itself is a function of time. Okay, so drag force will also turn out to be a function of time. Okay, now finally, let us just say that why did we call it as this wake survey method? So what is why is this method like we are using our conservation equations itself, but why do we give a separate name to this method? Is because this is how people were measuring drag, and what is so important about this is you can see that nothing else matters. What matters is I should know only two things. So I only should know what is the velocity distribution in the wake region. So once I measure the velocity distribution in the wake region, and if I assume that this is a large enough thing, and of course I need to know what is my u naught. U naught is a uniform flow which is already given to me, or I have already sort of measured that, assuming that I know that. Okay, I put it in the wind tunnel where the flow is coming in with a certain velocity. So I know what is my u naught, and then for that u naught I just measure the wake. Okay, I just take one probe, pitot tube maybe, and I just traverse it along the y direction at a sufficiently large distance from the object. So I measure u as a function of y. Okay, and then I just use this equation to find out what is the drag that is going to be experienced, that is being experienced by this object. Okay, so that's why we call it as a wake survey. Just survey the wake, and knowing the wake, we can find out what is the drag on this object. Okay, is this clear? Of course, we have not talked about how to find forces along the vertical direction. Can we find out forces along the y direction here? Yes, I mean, we can. In principle, there is nothing wrong with that. We can use, then we will have to do the same thing now. Whatever we are doing along the x direction, we will have to do things along the y direction. In this case, that exercise is futile, because I know that because of symmetry, there will be same amount of mass which is going to be there on both the sides, and therefore these two momentum are also going to cancel out. Okay, so there is no point. So there, and we know that there is no net lift force on this object. There will be a time varying lift force. Okay, so going back to the question that was asked, it is, there will be a time varying lift force that will be there, but there will be no mean lift force that will be there on this object. Okay, is this clear? Okay, so we'll move ahead from here. So we have essentially gotten our Reynolds transport theorem, and from there we have looked at getting our mass conservation equation, momentum conservation equation in integral forms, and we will do a small exercise homework where we will be using these equations in a more detailed manner. I just gave you one example as to how we use these equations, and the good thing is that this method is also like a standard method, the wake survey method. Now we will move on to the differential form of these equations. So before getting into that, we will have to introduce a small topic, deformation of a fluid element. So again, I'm assuming people at the back are able to see whatever is being written on the board, right? And able to hear me clearly. So let us say that I have a fluid element. To begin with, I will assume that it is nice rectangular. The sides are A, B, C, D. So this is a fluid element. So this was moving as a function of time. So let us say that this is a picture at time t is equal to 0. Now, what are the velocities? So let us say the velocity of A is u comma v. So I would like to know where will these points go after some time delta t. Okay. So of course we would know that, okay, this point will A will move somewhere here, B will move something like this, D, and so it could be moving something like this here. A, B, C, D can become A prime, B prime, C prime, and D prime after at time t is equal to delta t. So I'm interested in finding out the displacements, all these displacements, and see what is happening. So let us, as we said, the velocity of point A is u comma v. I'm doing it in 2D, we can do it in 3D. Of course, 3D is far more difficult to visualize. So we will just restrict ourselves to 2D, and we will see that the same thing can be then generalized into 3D without actually doing it. So if I know what is the velocity at point A, what is the velocity at point B? Okay, assuming that this element has a size delta x and delta y, and of course our coordinate axes are x here and y in the other direction. So can we say what is the velocity at B? So we can use just Taylor series and say that if velocity at at A is u comma v, then velocity at B would be whatever is A. So I'm just going to expand it out about A, okay, in a Taylor series. So I say that this is u do x times delta x comma v plus do v do x delta x. Okay, everybody with me? I can do the same thing for point D, C, but I will not need that. So I will just go to D. So D, what is the velocity at D? U plus. Okay, I want you guys to tell me what is the velocity at point D? Do u do y times delta y. And what is the v component velocity? V plus do v do y delta y. Everybody with me? So what is my A prime displacement, and displacement is along x and y. So I will just say first what is the displacement along the x direction. So what is this? So this is u delta t. Okay, let me just be consistent and use the same delta. So it is just a small delta t. So u times delta t, and this is my displacement along the x direction. A prime along y is equal to v delta t. Similarly, I can find out what is my b prime x. What is that? Again, whatever is the velocity of point B times delta t. Okay, so it is u plus do u do x times delta x, all of this multiplied by delta t. Similarly, b prime y is equal to v plus do v do x delta x times delta t. Similarly, I can write it out for d. U plus do u do y delta y times delta t d prime y v plus do v do y delta y times delta t. So I hope there is no mistake here. Okay, so if I have to just see that, okay, this is what was there at time t is equal to 0 and at time t is equal to delta t, the object has become like this, where I can find out the coordinates of all point with respect to wherever I was earlier, okay, and in this manner. So this is just a mathematical way to sort of say that, okay, this is what is happening. Now what I will do is give you a physical picture, and then we will connect, and that will give you a very good sense of what is happening. Okay, is this clear? First, the mathematical picture is clear. So what we have done is simply said that the velocity of point u is point A is u comma v, and knowing that I am able to write out the velocity of all the other points because this is a small element. And if I do that, then I can find out the displacement of each of the points. That's essentially what we have done. So we will call this as a mathematical picture. Okay, it just gives us the new coordinates, okay, in a purely mathematical way. Now let me introduce a physical picture, and The physical picture is that if I look at any element, how can it deform? So, if I look at deformation of fluid element, it can essentially do four things. So, I can take this element and this element deforms like this, it becomes bigger. Okay, so this is one option. The other thing that it can do is, okay, it could just, first is translation, okay, it just translates. Okay, so this is deformation, dilation. Then it can also rotate. So this is my element, and after some time delta t, it just rotates. And becomes like this. And the fourth thing, so this is my rotation. The fourth thing is it could shear. So this means that this face has come like this, has moved up, and the other face has moved towards the right. So these are the four ways in which the object can actually undergo deformation. So this is my, we just call this as deformation. Here the object has sheared. In the other case, the object has translated. Here it is translated, here it is rotated, and in the other case it is just dilated. Okay, and it could be like dilation in one side, compression in the other side, all that can be adjusted, all that is covered here. Okay, so we have done it in one case, but of course it could be the other way around as well. Okay, so these are the four ways in which we can have the object actually deforming, that can happen. Actual deformation of an object can happen. Okay, so these are the only ways. I think this is just physically, we just think about it and we say, okay, this is all that can happen. Just like in our Reynolds transport theorem, we said, okay, they are the only thing that can happen to people in a village is that births and deaths, or there could be migration. There is nothing else that can happen, and therefore this is how we can write out the balance of the population. Okay, same thing we are saying here. Now these are the four physical things that can happen, and everything I have now accounted for. So the question arises that earlier we had this picture, which is what it was saying, and now this is the picture that we are saying. Okay, and it is very clear that both these two pictures should not be the saying different things. That means that both of them should be saying the same thing, and we will have to just look at how exactly they are saying the same thing. So we start identifying where these modes of deformation are. So maybe we start off with translation. So in translation, what happens is the object just moves without changing its shape. Okay, so how much would it move? So if I have to find out the translation part of it, I will say that the translation part is point A is, or I know, is moving by u times delta x. In the x direction, it is moving v times delta, not delta x, u times delta t along the x direction and v times delta t along the y direction. This is how my point A is moving. Okay, so I should have something similar in for the other points as well, B, C, and D. Okay, so can we identify that? Okay, so you can see that this point B, which is moving by u times delta t, okay, this is the, you can see that this part is the translation part of it. Okay, so this is the component. So if I just look at u times delta t, this is what is saying that this is how much translation is happening along the x direction for point B, and similarly v times delta t is the translation of the point B which is happening along the y direction. Is this clear? Now when I look at point D, it's again I see u times delta t and v times delta t, okay, which is also, so you can see that this is how much everything is translating. So what we are doing now is just sort of eliminating or trying to understand these from this physical picture, what are the corresponding terms that I am seeing here, and I can see this term very easily. This is the translation part. Now what about the dilation? What does dilation mean? The dilation means that this point B has moved by an extra distance, right? And D has moved, and it has moved an extra distance along the x direction, and B has moved an extra distance along the y direction. So how much is this? You can say that this is going to be because of the difference in the velocity that is going to be there between the two points, and this extra velocity is dou u or dou x times delta x times delta t. Okay, this is the extra component of velocity that I have, and then if I multiply it by delta t, that will be the extra amount of dilation, extra amount of movement that the point B will experience. Okay, and similarly this point D would experience an extra velocity which is dou v dou y times delta y times delta t. So this is the amount of extra velocity that the point D would experience, and therefore we will see that this is my dilation that would happen. And we can see these terms in our equation. So this term is already accounted for. This term is accounted for from our translation, and this part is now being accounted for. This part in B and this part in D. Okay, you can see that we are not equating everything. This part is still not accounted for. Okay, is this clear? So what it is telling us again, that we have been able to look at two simple modes and identify, as we said, that the physical picture and the mathematical picture should be describing the same thing, because in general what we are saying is an element will undergo all of them, and therefore I should be able to just superimpose all of them. So I can say that, okay, the total deformation is because of dilation plus translation plus rotation plus this deformation, pure shear that is there. Okay, so I can, if I combine all them, that is my total deformation that I have, and that total deformation is going to be given in this manner here. Okay, so we are saying exactly the same thing, and we are just now trying to figure out how each of these terms are turning out to be. So now what we are left with is the rotation and the other part. So let us say that this rotation is by an angle delta theta. So how much is this movement here of this element? Is delta theta multiplied by delta x, right? So this is the arc length and this is my angle. So the arc that I would get is your delta theta into delta x. And here this is my pure shear. So in pure shear, so this is my angle alpha, let us say delta alpha. So this angle is also delta alpha. This angle is also delta alpha. So how much is my delta alpha related to? So this delta alpha is taking this point up by an amount which is delta alpha into delta x. Correct? That's how much this point will move in along the x direction, and here it is moving by an amount which is delta alpha into delta y. Okay, and here, as we said, this is moving by delta theta into delta y, and here we are moving it in the y direction and the negative direction. So what we are now saying is that if I look at the movement of this point B, okay, this is movement along the y direction. Okay, here also it is happening along the y direction. Okay, and I will have to now look at this component which is remaining with me and equate the two things, right? So I can say that BBY remaining, which was your dou V dou x into delta x into delta t is equal to, in fact, I should correct myself a little bit. You would like to have this angle divided by 2 here. Okay, so the total amount of shear that I get is delta alpha, and so therefore each of these two angles is delta alpha by 2. So I get the movement of point B along the y direction, okay, is only happening because of these two modes. You can see that there were no contribution of the deformation or the movement of point B along the y direction from these two modes. Okay, so it's only coming from these two modes. Okay, and how much it is? It is delta theta times delta x and plus, so I should put it by 2 here, by 2 here. It is delta alpha upon 2 times delta x. So this is, you can say, one equation that we have gotten, because you can see that there are two unknowns, theta and alpha. I need to write out two equations. So this is the first equation that I have gotten, okay, which is corresponding to the movement of point B along the y direction. Similarly, I can find out what is the movement of point D along the x direction now, and what is remaining is this term here, okay, which has not been ticked. Okay, so it is dou u dou y times delta y times delta t, and that is equal to the movement which is here is this minus delta theta delta y and plus delta alpha by 2 times delta y. So this is my equation number 2 that we have. Okay, so now we have two equations and two unknowns, and we can solve for them, eliminate delta x. So first of all, it is easy to see that I can cancel out my delta x from this equation, delta y from the other equation. And then if I add up these two equations, my delta theta will vanish, and I will get dou u dou x plus dou, dou, dou u dou y plus dou v dou x into delta t is equal to delta alpha. This is what I will get by adding. So equation 1 plus equation 2 leads to this equation, equation. And if I were to subtract out 1 from 2 or 2 from 1, so 1 minus 2 gives me dou v dou x minus dou u dou y times delta t is equal to twice of delta theta. Okay, everybody with me? Any questions here? Any questions here? So what have we shown here? Okay, so we have essentially gotten our two angles, delta alpha and delta theta. We can divide them by time. So if I call this as equations 3 and equation 4, then I get delta alpha upon delta t is equal to dou v dou x plus dou u dou y, and I get 2 times delta, or maybe just take 2 on the other side. So delta theta upon delta t is equal to half of dou v dou x minus dou u dou y. Okay, so we will call this. Okay, so this is easy to see. This is my rotation. Rotation angle was theta. So this is, what is delta theta by delta t? Is the rate of rotation, angular speed maybe. So we can call this as omega. Use omega here, and we will put this as a subscript which will be about what axis is it rotating? About the z axis. So that's why we will keep a subscript z in here to emphasize that this is a rotation about the z axis. Yes.
Now we're rotating about point A. If the pivot was somewhere else, in the fluid element, then we have to.
So, okay, so that's a good question. So what we are saying is that when we were looking at this picture, we said that this is a pure rotation. Pure rotation is happening about the point A, as you just said. Okay, and in general, it is a combination of all of them. Okay, and what we have done by this analysis of putting maths in, and physics in there, or physical picture in there, and then combining the two things, is to be able to see what term corresponds to what is the physical meaning. Otherwise, in this equation, whatever we had written earlier, all the displacements, we don't know what it means. So now what we were able to do is to identify what meaning is corresponding to each term, right? I see a lot of blank faces. Why? People are not following? Just too simple? Too difficult? Yes, no, already seen, too trivial? Is it too trivial? It's already done. We can always go to something else if this is too trivial. Yeah.
Kind of difficult to relate the four physical phenomena with the six equations or six terms below.
So that's why you should have stopped me there, no? So we just said that if I look at, see, I have removed all those equations here. So, but we said, okay, if you were to look at AA displacement of, okay, we'll have to write it out again. So if I look at the point B prime along the x direction, what is this? What is this displacement? So we are saying just take the velocity of point B, okay, multiplied by delta t, and then you will get this displacement. Okay, and here, because we are looking at displacement along the x direction, I am only going to look at the velocity of the point B along the x direction. And how much was that? It was u plus whatever is the derivative, because u is the velocity here. So whatever is the velocity here is u plus the gradient multiplied by this increment, right? So that is my velocity here. Okay.
Exact relation of each term is giving the physical.
Okay, so let us just write it out once more very quickly. So this is the displacement that we got along the x direction for the point B. So here we say that u dt, u delta t is there, and we can see that that is there in all the four terms A, B, C, D. So that is a simple translation, because there is no gradient, nothing. It's like if I just take A, B, C, D, and if I only give this, then the whole this, yeah, this rectangle will just translate, right? Now the other thing we said is that if it is dilation, this dilation is going to happen only if the velocity at this point along the x direction is more than the velocity here. So that is my component dou u dou x, okay, and of course multiplied by delta x. That is the extra velocity that I need to have here, and of course that multiplied by delta t is because we are looking at displacements. Okay, similarly for the y direction, so you can see that this is the component that we now get. This component is now corresponding to the dilation term. Okay, similarly in D, so point B is moving along the x direction by an extra amount, okay, and D is moving by an extra amount in the y direction, and we could just relate that because there are only two terms here. One we have already said it is translation, so this is the second only term which is there, and it also connects very well with whatever we can understand physically. Okay, so the B I have already taken care of, B along the x direction. So B along the x direction is already taken care of. So B along the y direction, when we look at B, displacement of B along the y direction, it is this is what we get, okay, and this is already accounted for from the translation. So this is what is left, okay, and this is what we are so this is movement or translation of B along the y direction. Okay, so how much is, and we can see that the rotation is moving the point B along the y direction, okay, as well as this pure shear is moving the thing along the y direction. Okay, so I just write out, so and then we say that the total that I get here will be the sum of these two. Okay, so I just add up those two things, and similarly I do it for the point D. Okay, in D also only one term remains, okay, which is along the displacement of point D along the x direction. Okay, so if I do that and equate it, this is what I get. Okay, and here we realize that when we have rotation, rotation is taking the point D along the minus direction, and the shear is along the plus direction, and therefore these signs are different. For B, both of them are taking it along the same direction. B is always moving because of rotation, it is moving in the plus x direction, and the pure shear is also moving it along the x direction, and therefore both of them have to be added up, and here they come with opposite sign in for point D. Okay, so then we eliminate our, or then we can find out how much is my rotation. That's what we did. After that we said there are two equations, two unknowns, and we solve for them. Okay, and what we get is something which is very interesting, which is where we are now, which says that the rotation, how much is the rotation of this element? It is going to be found in this manner here. Okay, so why did we do all this exercise? Is sometimes we are given that this is my rotation, we never connect it to the basic deformation of the or displacements of the elements. Here we can do that very clearly, very nicely, and we can see a very clear physical picture and a mathematical sort of a description of that. Okay, so that's why this whole derivation I like, because it is very transparent. It gives you very, very nicely, very clearly as to what is happening to the fluid elements. Okay, and this one now we are going to say it is deformation, I mean, or pure shear. Okay, and we are saying that this element is shearing in its plane itself. Okay, so if I just use the term gamma, or symbol gamma dot here, and we are just going to say it is gamma dot xy. Okay, and this is happening in the plane. Okay, and of course it's a time derivative term, so it's a dot term. So I've just to emphasize that I put a dot in here, and yeah, and everything is happening in the plane. So is this clear? Better now? Okay, so this this idea of deformation of fluid element is very important. Okay, because it brings out the idea of rotation of fluid element, which we will call that as vorticity when we go to the vorticity chapter. Okay, this is actually vorticity, and the other one is pure deformation, and this deformation will get connected to your stresses. Okay, so we'll see that the because of this deformation there is a stress, and that is going to be viscous stress if I multiply this deformation by mu. So that will become my stresses that the fluid will undergo. And then that will enter into the momentum equation. So we just took a small diversion and showed this relationship between stresses and the velocity gradients and so on. Okay, so that when we go to the next part, we will be able to simply use this relationship, and we now know where these relationships are coming from. Okay, so I think this is where we will stop for today, and in the next class we will continue with this, and we will complete our derivation for the mass conservation equation as well as for the momentum conservation equation, and for the momentum we will get the Navier-Stokes equation in the differential form.